The topic I'm going to talk about today is a joint work with Robert Benda, Eric Cancès, and Benjamin Stam. And here what I'm going to talk about is what we kind of understood from a mathematical point of view about partition scheme of a molecular electronic density into some atomic contributions. So there is a very wide zoology of methods in order to do so, to compute such partitions. I'm going to explain in a moment what I mean by that. And what we did was to try to kind of understand at least some of these, some points about some of these, with a view to try to design some more accurate and efficient numerical algorithms in order to compute these partitions. So today I'm going to tell you about what we understood there and what still remains to be understood at this point. So first of all, I'm going to explain why we were interested in this problem. Why are these partitions interesting for MD and quantum simulations? And then most of my talk will be more specifically focused on one particular family of methods, which is called the Iterative Stockholder Atom method. And I'm going to explain to you what it is about. And also about numerical algorithms in order to solve the quantities given by this method, the partition given by this method. And then I will show some numerical results on some simple systems to compare the different numerical strategies that are used in order to address this kind of iterative Stockholder atom methods, which is I will call ISA to be more quickly. So let's begin with the context. And what do I mean by these partitions? So here I'm going to consider a molecule composed of n electrons and m nuclei. So the nuclei will be located at some positions which will be denoted by R1, Rm, which are three-dimensional vectors. And their nuclear charges will be denoted by Z1 up to Zm. And I'm assuming here that I'm given some molecular electronic density for this molecule, so which will be denoted by a rho, okay? So you can imagine that rho is an output of any calculation techniques that you like, for instance, a DFT calculation, okay? And then it will be a non-negative function defined over R3, and its integral over R3 will be equal to n, the number of electrons within the molecule, okay? In the following, I will need to make some extra assumption on this molecular electronic density that can be relatively easily satisfied for a lot of practical systems. I will need to assume that this electronic density is a function that will belong to some functional space which will be denoted by x in the talk, and namely which is a space of functions that are integrable over R3, that are bounded as well, that goes to 0 at infinity, and with finite first-order moments. Okay, so for many systems, electronic densities or molecular electronic densities can indeed be shown to belong to this particular functional space X. So that will be an assumption that I'll make all along of the talk. And so what do I mean by having a partition scheme into atomic contributions there? So here, this partition are also called in the literature atoms in molecule decomposition, so AIM as a shortened denomination. And what is this about? What you wish to do, given your electronic molecular density, you want to decompose it under this form here. So as a sum from A going from 1 to M, remember M is the number of nuclei within my molecule, okay, of functions here, which I denote by rho A opt, okay, of R minus RA. Remember RA is the locations of the atom A within the molecule, okay, and what do you want about this particular function, rho A opt? You want it to be non-negative and to be as much as possible localized around the 0 point, and to be somehow optimal in some sense in order to represent the local contributions of atom A to the electronic molecular density. Okay, so just to have a schematic 1D picture, okay? So assume that you've got a molecule with 3 nuclei that are located at this point here, okay? So here you've got R3, for instance, R2, R1, just to have a very simple picture. Your electronic density will typically look like this, okay? And then you would like to split it under this decomposition with 3 local atomic contributions that may look like this, for instance. Okay? Up. I'm sorry, this one. So typically, this violet curve will be rho 2 opt of R minus R2, and so on and so forth. Okay? And of course, there are lots and lots and lots of ways of decomposing such a molecular electronic density under this form here. And what is an optimal way of finding such a decomposition is a very post problem in general. Okay, there are various ways to define what is optimality in this sense, and I'm just going to talk about a few methods that are quite popular in the chemistry literature to do so. Okay? But first of all, before talking about AIM decomposition and the way to get them, you may ask, but why do we use such a decomposition, of course? And actually, they are useful for many purposes, but in particular, it enables to compute a set of local descriptors of the molecular electronic density that are used to field some force fields in MD simulation. Okay, so for instance, one of these, the most simple kind of local descriptors are partial charges of atoms within the molecule. Okay, that will be given typically as the integral of the A proatomic densities over R3. Okay, so it enables to see if some molecule polarize or not, for instance. And a lot of classical force fields like amber, charm, gromos rely on the use of these partial charges in order to define some force fields. But in other more advanced force fields, polarizable force fields, like the one used in the amoeba code, for instance, you may use higher order dipolar moments of the local contributions of the atoms within the molecule. So like some first order or second order local dipolar moments. And so having such AIM decompositions enables you to compute these kinds of local descriptors and to feed in your MD simulation code. But then you would say, okay, but why bother about computing such a full AIM decomposition if you're only interested in having a finite number of scalar local descriptors? And indeed, in many codes, these quantities, partial charges or local dipolar moments, are not computed using AIM decomposition. They are computed using different ways. There are different kinds of approaches there. For instance, they can be determined indirectly in so-called electrostatic potential methods. So the most simple versions of these methods consist in the following way. You may optimize the value of just the partial charges of each atoms within the molecule so that the resulting atomic electrostatic potential that is computed just by assuming that you've got point charges, located at each of the nuclei is as close as possible to the exact quantum electrostatic potential. So that's a way to do so. That's an approach, and there, so you have to solve some kind of optimization problems to get these partial charges. Okay, and you can do the same if you want to add also higher order dipolar moments as well. Or you could use some direct ways of computing these charges by using, for instance, like in the Mulliken-Lovetin population analysis method, you make use of some coefficients of the density matrix of your system in order to compute such partial charges or such local dipolar moments. Okay, so in the amoeba code, the method which is used in order to compute these guys here is the so-called distributed multiple analysis method, which falls into this kind of direct methods, approaches. Okay? What was observed with such approaches, which avoids computed AIM decompositions, is that they are observed to be quite basis set dependent. What do I mean by that? For if you're doing your DFT calculations, of course, what you would like to do is if you use some basis sets whose the dimension of which grows and increases, you would like these values of the partial charges and all the dipolar moments to converge at some point, okay, with the dimension of the basis. However, this is not always guaranteed, and I'll show you in a numerical test later. For instance, for this DMA method, that we have surprises as the dimension of the basis increases, which is not, of course, a desirable feature, okay, of this kind of approaches. And in contrast, so many methods based and this full AIM decomposition I've just told you about are observed to be much less basis dependent. So it's kind of a numerical observation, and so somehow these methods, of course you need to compute more things, but they seem to be more stable with respect to numerical discretization. So that's why we were interested in understanding some of these approach. So let me remember what I meant by an IAM decomposition. So what I want to do is now to find a set of M atomic local electronic densities, which are as much as possible localized around zero, and which enable to represent my full molecular electronic density under this form here. Okay? And I want them to be optimal in some sense, hopefully in some physically relevant sense. So, for instance, so that computed partial charges are as close as possible to what is observed for the molecule. Okay? And how to define, as I told you right before, how to define what is a good optimality criterion with respect to this is not very clear. Okay? And so this gives rise to wide zoology of AIM decomposition methods depending on the optimality criterion that people consider. Okay? So here, the ISA approach is one of these AIM decomposition methods which uses some kind of optimality criterion, which appears to be a nice one, but why is it a nice one? It's a mystery. Okay? It was in particular studied by Paul Ayers and Lillestolen and collaborators. And this last paper by 2017 is a nice review about this kind of family of methods. So let me explain to you what this ISA method about. So first of all, I need to introduce a few notations. So remember, X was the set I assumed my molecular electronic density to belong to. I will use the notation X plus to be the set of functions belonging to this functional space X that are non-negative. Okay? And let me introduce this set K. So this set K is a set of admissible AIM decompositions. So it's a set of M local atomic electronic densities, which will all belong to this set X plus, and which satisfies this relationship, this AIM relationship. Okay? I will need to introduce a few more notation. For a given element rho A, which belongs to the functional space X, rho AS here will denote its spherical average, which is defined as follows. Okay? Where here S2 is a unit sphere of R3. So, by definition, the spherical average, rho AS, is a radially symmetric function. And in addition, it satisfies the following charge conservation property, that the integral of the spherical average of rho A is equal to the integral of rho A. Okay? So what's the general principle of most AIM decomposition methods? It's the following. The optimality criterion that will be used in order to define these local atomic contributions in an AIM decomposition will be the following. We are going to try this rho A opt to be as close as possible in some sense to their spherical averages. You want them, remember, these local atomic contributions, you want them to be localized around zero as much as possible. And here, in this family of methods, what you're going to say, I want this rho A opt to be as close as possible to their spherical average, to some radially symmetric functions, and so they're the spherical average. Notice, however, that in general, this rho A opt, these local atomic densities, will not be radially symmetric. They will be close to, but not exactly radially symmetric. Okay? And so, this ISA method, it falls into the family of so-called entropy-based AIM decomposition method, which consists in defining optimal local atomic densities as solution of some minimization problem here, which writes under this form. So you look for a bold rho opt, which will be the family of all local atomic densities, as a minimum over all possible admissible AIM decompositions of some functional here, which writes as the sum over A equal 1 to M, so as the sum over all atoms within the molecule, of some quantity here, which I denote by S of rho A with respect to its spherical average. And what is S here? S of F with respect to G is a quantity, which is usually some kind of relative entropy, which measures the discrepancy between two functions f and g in x plus. Okay? So what you want to minimize this quantity, and this S of F with respect to G kind of measures the discrepancy between f and g. If you want to minimize this, you somehow, in some sense, depending on the choice of S, enforce that the rho A has to be close to their spherical averages. Okay? And in the ISA method, one particular choice of entropy functional here, the particular choice, of entropy functional which is done here, is the so-called Kullback-Leibler divergence, which is defined as follows. For all function fg, so this S of f with respect to g, will be equal to the integral of f of r times the log of f of r divided by g of r. Okay, so it's a functional which is very much used in information theory. Okay, and it has very nice mathematical properties I'm going to talk about. Okay, but there are many other choices in the chemistry literature. So this one is one of the most popular, but other choices that could be made are based on other kind of distances or relative entropy. And for instance, in this paper, they use the so-called Ellinger distance, which is defined as follows. Okay, so I'm mostly going to focus on this particular case because we are able to show some mathematical properties that are quite nice, especially for numerical methods. But it's one method among many others. So I need to make a few remarks that are quite easy to do, but which are central for the rest of the talk. Here I will denote by XR and respectively XR plus the set of radially symmetric functions of X, or respectively X plus. So remember here X plus is just a set of functions of X that are non-negative. So here XR plus is just a set of radially symmetric functions that are non-negative as well. So the following result is quite simple to see, okay, but it's central. Let rho A be an element of X plus, a non-negative density. Then if you look at this constraint minimization problem, which amount to finding the optimal radially symmetric functions, which is non-negative, rho A0, which minimizes this Kullback-Leibler divergence of rho A with respect to rho A0, among all the possible radially symmetric functions, such as its integral is equal to the integral of rho A, then it has a unique solution, and it is the spherical average of rho A. Okay, so it's quite easy to check, and it's central for the rest of the analysis. Actually, this simple, of course, this was done way before we were interested in the problem, but when you do this observation, you can equivalently reformulate this minimization problem, the ISA minimization problem, in another formulation that it's much more convenient for the mathematical analysis, and which is the following one. Actually, what you can show is that you can express the solution of the ISA minimization problem by considering this other minimization problem, which here consists in finding a set, the optimal set of local atomic densities and a set of local atomic radially symmetric densities, which is denoted here by rho 0 opt, that minimizes some functional, which is denoted by big S of rho 0, over a set of couple rho 0 that belongs to this set here. So let me first explain what is the set, and then I go to the definition of the full functional here. So here rho is a set of local atomic densities that are not necessarily symmetric, and big rho 0 is a set of radially radially symmetric atomic densities. And this C as set is the set of couples, rho and rho 0, such as for all atoms within the molecule, the integral of the radially symmetric function is equal to the integral of the non-radially atomic density. Okay, so you have to satisfy here this charge constraint between radially symmetric functions and non-radially symmetric functions. And here, the functional that appears here, well, it's just the same functional as before, except that you define it as being the sum from A equal 1 to M of the Kullback-Leibler divergence of rho A with respect to rho A0. Okay? And then what you can prove is that this problem is equivalent to the first one in the sense that, well, first you've got, there exists a unique solution to this optimization problem. The rho opt, which appears here, is then the unique solution of the original ISA problem, okay? And the rho 0 opt that appear here, which is a set of radially symmetric functions, well, it's simply the spherical averages of all the atomic contributions of the rho, which belong to the rho opt. So of the solution of the ISA minimization problem. Okay? So considering 2 or considering 1 is equivalent. So, okay? But this second formulation, which is more complicated because you've got 2 sets of unknowns to minimize upon, actually is better for the mathematical analysis of the numerical algorithms I'm going to present to you. Okay? And that precisely, so here it's not very surprising results. Everything is convex here. The only thing that is a bit tricky from a mathematical point of view is because you may lose some compactness in the minimization problem, but it's not very, it's not a surprising result. It's kind of easy remark. So yeah.
So there is no smoothness explicitly built in.
No, not.
It automatically.
So we can prove some smoothness properties for diatomic system. We've got partial smoothness results just for diatomic systems. And I agree, this is definitely a desirable property you would like to have on this optimal electronic density. At this point, it's not that easy to get for general systems.
But intuitively, is there any mechanism that just by minimizing the scale divergence gives you a smooth file? Yeah,
that's what you expect. So from the numerical side, I'm going to show some results. Indeed, you obtain some smooth profiles, but we did numerical tests so far only on on simple molecules. For larger molecules, whether this will still respected, it's not obvious. So that's why I'm also insisting on the fact that this is one choice. Is it the best one? It's clearly it's not clear. It's just a popular choice where we've been able to see things. But here, indeed, nothing is guaranteed at this point. Okay, so that was, let's say that this minimization problem, so the ISA problem, is kind of the reference numerical algorithms are going to compare to. Okay, basically, all the ISA numerical methods, they wish to approximate these guys here by one way or another. Okay, and so there is one algorithm which can be defined on the continuous level. Okay, which is called the ISA algorithm, which has already been proposed in the chemistry literature, but which was not interpreted in the way I'm going to present it to you now. Okay, and the way I'm going to present it to you now was actually a good way of seeing this already existing algorithm in order to understand its properties. So it's this ISA algorithm, actually, you can interpret it in the following way. It's actually, you can see it as an alternated direction minimization associated to this formulation of the problem. So what do I mean by that? You start from a given set of n radially symmetric functions, which I denote here by rho 0, 0. Sorry, it's an iterative algorithm. I forgot to mention that. And that you just use some kind of fixed point method, which reads as follows. At iteration m, you define rho m a set of admissible IAM decomposition. So the components of this rho m are not necessarily radially symmetric, which minimizes this entropy functional S of rho with respect to rho 0 of the previous iteration, m minus 1, so over the set K I introduced to you before. And then in the second step, you define the new set of radially symmetric functions, rho 0 m, as the solution of this minimization problems. Now you know rho m. So it amounts to minimizing this entropy function, S of rho m with respect to rho 0, over the set of radially symmetric atomic functions that have the same charges as rho m. Okay, so such that the integral over R3 of rho A0 is equal to the integral over R3 of rho AM for all A. Okay, and so actually, what is nice is that you can explicitly express the solutions of these two steps of the algorithm. This works as follows. So for the sake, I'm going to begin with step 2. So step 2, I'll just rewrote the minimization problem here. Actually, if you look at it closely and you use the form of the entropy function on S here, actually, you can compute its solution by solving m-independent problems. Okay, sorry, up. For all A between 1 and m, actually rho A0m is the minimizer of this problem here. You want to find the radially symmetric function, non-negative functions, that minimizes this callback Leibler entropy under the constraint that the integral of rho A0 is equal to the integral of rho AM. And from the previous observation I told you about, automatically it gives you that the unique minimizer of this problem, rho A0m, is the spherical average of rho AM. Okay, and this is the case for all A between 1 and big M, and I use this shorthand notation. Okay. Now let's go to step 1. Step 1, Step 1 consists in finding rho M. So it's a set of local atomic densities that are not necessarily radially symmetric, but which belong to the admissible set of AIM decomposition, okay, so which are related to my original molecular electronic density, which minimizes this problem here. And actually, this rho m can be also explicitly known, okay? So this was known in the literature before us. Actually, if you fix rho 0, the optimal rho solution of this problem here reads as follows. I will denote it in the following by G of rho 0, okay? And its components associated to atom A is given by the following formula. GA of rho 0 is given as if rho 0 of R is non-zero. It's given as this formula here, rho 0 of R divided by rho 0 of R plus RA times rho of R plus RA. Rho is my original molecular electronic density, okay? And this rho 0 guy is defined by this formula. It's the sum for over all atom of all these radially symmetric contributions, but shifted with respect to the position of the different atoms in the molecule. Okay? So here at this point, just remember, solution of this problem here can be computed explicitly with such a formula. And I just gather this, under this G notation. Okay. And so then this ISA algorithm, so that was the way you could find it in the chemical literature. It only boils, it's quite simple to write, it only boils to considering this fixed point algorithm by defining at each iteration n rho m as being G of rho 0m minus 1, and rho 0m to be the spherical average of rho m. Okay, and you iterate like this. Okay. And so one of the questions that we were wondering about this algorithm is, does it converge to the true solution of the ISA problem? Of course, so that's a natural question. So at first sight, it is not obvious that it will converge. Where is the difficulty? So difficulty comes from here, from the step 1 here. Where see here in the set where I choose these local atomic densities, I'm not imposing the constraint that the charge of these local atomic densities should be equal to the radially symmetric set of functions that appear here, rho 0 and minus 1. It only appears in step 2 of the algorithm. So in particular, it is not obvious, for instance, that the entropy functional should be a non-increasing quantity as the iteration of these fixed point algorithms increase. Okay? But actually, it turns out to be the case because of specific properties of this Kullback-Leibler entropy functional. And so this is a nice feature of this algorithm, which, at least up to our knowledge, was not had not been theoretically remarked before. Of course, it had been seen on numerical observations. And these algorithms provide a set of local atomic densities and symmetric and their radially symmetric counterparts, such that this entropy functionals is non-increasing as the iteration of the fixed point loop increase. And moreover, what you can show is that if you look at the difference of this entropy between two successive iterates of the algorithm, then this bounds some quantity, which is equal to some constant, times the sum of all the L2 norm squared of the difference between two iterates of the local atomic densities. Okay? And in particular, it says that the norm between two successive iterates given by the algorithm will go to 0. This is not enough to guarantee that the algorithm converge. And here at this point, we are still stuck. Probably for technical reasons, but on the algorithm defined on the full continuous level, we still can't get convergence of this algorithm to the solution of the exact minimization problem. So this may be technical, but there is some gap in there's still some remaining gap theoretically there. However, there is another version of the algorithm, which will be an approximate version of the algorithm, kind of a discretized version of the algorithm, where we are able to prove such convergence results. So let me explain what I mean by this. So here, that was kind of our motivation for introducing this approximate optimization problem, which we call LISA problem, okay? Which is an extension of a method which existed in the literature under the name of VAR method. Okay, we realized this later. And this discretized version of the LISA problem reads as follows. Okay, it's a very simple way of discretizing things. For any atom A, let Na be some positive integer, and let GA1, GA, and A to be a set of functions that are radially symmetric and non-negative. Okay? I'm going to assume for the sake of simplicity that these functions are also normalized, L1 normalized. So you can think of these functions here as being some Gaussian basis sets, for instance. I will denote by for all atoms, I will denote by VA the span of these basis functions, and VA plus what I denote by span plus some of these functions, which is just a set of all linear combinations of these functions with non-negative coefficients. Okay? And I'm going to define another minimization set, CL-ISA, which is a counterpart, discrete counterpart of the C-ISA set I've introduced you before. Okay? And it will be the set of couples rho 0. So rho, remember, is a set of local atomic densities, not necessarily radially symmetric, and rho 0 a set of radially symmetric local atomic densities, such as rho is an admissible IAM decomposition of my molecular electronic density, and rho 0 here, instead of being a set of any radially symmetric functions, non-negative radially symmetric functions, I assume them to belong to the Cartesian product of this set VA+, of this cone VA+. Okay? Which still satisfies the charge constraint, okay? Then the integral of rho A0 has to be equal to the integral of rho A for rho A. Okay? And then I can consider an approximate minimization problem, which is kind of a discretized counterpart of the original ISA problem I showed you before. And it consists in trying to find rho opt ELISA and rho 0 opt ELISA, which minimizes the same entropy functional, but this time over this set CL-ISA, where here I'm just considering this set VA plus instead of all the radially symmetric functions. And so you can prove that this approximate minimization problem still has a unique minimizer, provided that you make a particular assumption on these functions here, GA1, GA, and A. what is this assumption? You need to assume that for all A, for all atoms, if you look at the quantity rho of R plus Ra, where Ra, remember, is the location of the 8th atom, times the log of the minimum over all K of these GAK functions, this has to be some integrable functions over R3. What does it mean? It means, for instance, that the GAK cannot be 0 on some parts of R3. Okay? And it means also that this rho has to decay fast enough at infinity. For instance, if this assumption is satisfied, this rho decays fast enough, and this GAK are some Gaussian functions. Okay? And so you can write a very simple analog to the ISA algorithm, which is, but here with the LISA algorithm, which is also an alternated direction minimization algorithm, and it writes as follows. And here it's still a fixed point iteration. The only difference is here in step 2 of the algorithm. When you compute the radially symmetric functions here, you only look at them as solution of these minimization problems, and you want them, and they will not be any radially symmetric functions, but they will belong only to this Cartesian product set, defined by means of this Gaussian basis set. Okay? And so, as before, as in the original ISA problem, this step 2 can be decomposed into M-independent problems. Okay? Which reads as follows. Yeah?
You have some estimates between the two functions that you would find? I mean, the one where it's restricted.
No, and it's an open question, and we don't. Of course, it's very important the way you would choose the VA plus, and you would like to estimate the error depending on how you choose the VA plus. No results not at this point, but indeed it's a tricky. It's an important feature of this method, definitely. So here, like before, this problem in step 2 can be solved with M-independent problems. And for each atom A, so the radially symmetric functions will be associated to atom A at the nth iteration will be solution to such a minimization problem. In general, then, this rho A0M here will not be equal to the spherical average of rho AM anymore, precisely because we constrain rho A0M to belong to some particular con, spanned by a finite number of functions. Okay, remember, rho AM can be any non-negative function. Yeah. But nevertheless, you can solve this problem in practice if you decompose rho A0 on the basis of the Gaussian basis functions that you've chosen. It only amounts to solving a convex minimization problems to identify these coefficients under some linear constraints. So this can be done quite easily in practice. And there is a unique solution at each step. And here, in comparison to the full continuous ISA problem, we are able to say something about convergence of the algorithm. You still have the same property in the sense that the value of the entropy still decreases as the number of iterations of the algorithm goes on. We still have that the difference between two iterates in the L2 norm goes to 0. And you can prove there, because you've restricted the minimization set for this rho 0 to some kind of finite dimensional set, indeed converges to the unique minimizer of the approximate minimization problem. And this converges in some sense. Okay. So, question, we conjecture that it should be still the case for the full continuous ISA problem, but still not able to prove it. So here, I'm going to go quickly on this, just to mention the fact that there are lots of other ISA-inspired methods in order to compute this AIM decomposition. The most directly related to ISA method, which we came about, is a GISA, which actually can be rewritten as follows. You still have some iterative algorithm, where actually in step 2, you still have, the idea that you have to decompose the radially symmetric functions over a finite size basis set. Okay? But here instead, what they do is that instead of minimizing directly the entropy functional, they minimize L2 squared distance of the radially symmetric function with respect to 0m. Okay? So here, because they use such a quadratic function, these steps are much easier to compute. Okay? It just amounts to solving a quadratic problem under linear constraint. But you break the variational structure induced by the entropy function. Okay? And so you don't have any more that the entropy will be decreasing along the iterations, as you will see in the numerical tests. I just wanted to go quickly on this. We also were interested to compare with another version of ISA algorithm, which is called minimal basis ISA, which was proposed in this work, which it's a more evolved version of the ISA method, but it's still based on variational arguments, a bit similar to what I just presented. And here what they want to do, they want to decompose the molecular electronic density under the following form here, where actually what you look is to atomic local densities, rho AL, associated to each of the shells of the atoms A within the molecule. So it's more like, decomposing rho as a sum of atomic shell densities rather than just atomic densities. But I'm not going to go very much in detail, but the ingredients are very similar to what I presented to you before, just before. So we did some numerical results on some simple systems to kind of illustrate some of the mathematical results that we had obtained and to compare different approaches. Okay. And the codes are available on these GitHubs that Robert did. Everything was implemented in Python. And also something that I should mention, I presented you the version of the algorithm where the integrals were supposed to be exactly computed. Of course, in practice, you need to use some quadrature rules. And then to do so, Robert used some Gauss-Legendre radial points and some Gauss-Legendre angular points as well. And with this number of quadrature points here. Okay, so let's first have a look at what's happened for the LIH molecule. So here we only computed the ISA solution, okay, with a very, very large basis set which are spanned by some piecewise affine basis functions. And here, what Robert looked at, he wanted to look at the partial charges, how the partial charges and the local dipolar moments of the atomic contributions of the computed IAM decomposition evolves when you look at the dissociation limit of LIH. So as the distance between the two atoms goes to increases. So here he computed for each value of the interatomic distance, he computed rho using an FCI method with a small basis set, 631G. And here is what he gets. So this is the energy. So here it's a small basis set, so you've got typically an equilibrium interatomic distance, which is 1.7 approximately. And what he observed is that when you look at the partial charges of lithium, for instance, it goes to 0 as the molecule dissociates. So that's kind of reassuring here. And also what he could obtain is that at the equilibrium length, you've got a strong polarization of the molecule. And this also can be seen here on the first order local dipolar moment. Here what's represented is the component of this local dipolar moment in the direction of the dimer. Okay. Here, Robert compared results obtained by the ISA method with the DMA code that is used in MEBIA. So remember, DMA code doesn't compute an AIM decomposition; it only computes partial charges and local dipolar moments in some way. And he wanted to compare what was obtained on the H2O molecule with a molecular density computed with this method and various basis sets. Here, the idea was to check, as you increase the size of the basis sets, what happens to the partial charges and local dipolar moments that you compute for both approaches. So here, what can you see? Here you see there is this orange triangle and light blue triangles. These are the values obtained by the ISA method. And here, of the partial charges. And here, in the axis, here, the size of the basis sets increases. Okay? So what you can see is that these values of the partial charges indeed seem to converge quite nicely, even if the basis sets are not necessarily included in one another. And here is what happens to various flavors of the DMA method. Okay? Here you see, indeed, it seems there seems to be some kind of convergence, but which seems to be much slower than for the ISA method. So this is what happens to the partial charges, so zero-order dipolar moment method. And this is what happens to the first order local dipolar moment. Here, still, the triangle light blue and orange here are the quantities computed with the ISA method. So there seems to be at least some kind of convergence here as the size of the basis set increases. On the other hand, for the DMA approaches, for instance, let's take this set of red dots, you see it's kind of erratic behavior. So that's kind of illustrates what I was telling you in the beginning of the talk, that this kind of, at least for this DMA method on these particular systems, it's much more basis set dependent than the ISA, at least for this system here. And then Robert made some comparison of the various ISA schemes I told you about on some molecule. Here it's a CO molecule at this interatomic distance. And the molecular density was computed with this basis set and this and the restricted character fork. And here are the quantities that is computing here for the 4 different methods I told you about. As a function of the iteration of the fixed point algorithm I told you about, the value of the entropy functional. Okay? So here ISA is kind of a reference value for ISA computed with a large basis set. Okay? And LISA was obtained using a few numbers of quotient basis functions, which was the same used in the GISA method. Okay? So what you can see is that the MBISA, ISA, and LISA, which are all the 3 based on this variational structure with the entropy functional, indeed the value of the entropy functional is non-decreasing as the number of iteration increases. This is not the case for the GISA. This is the green curve here. I don't know if you can see, where there is no monotonic behavior of the entropy functional here. Okay? And what Robert also computed, because we don't have results on the rates of convergence for the LISA in particular, he computed here the error between the value of the entropy at iteration m and the final value of the entropy obtained at 40 iterations here. And here are the decays of the errors that you obtain. So in particular, for the ISA and LISA method, you see there seems to be some kind of very nice rate of convergence, at least for this very simple system. And Robert compared the values of the partial charges and the local dipolar moments that you can obtain at convergence, and the number of iterations that one needs to do in order to reach some common topic criterion. Okay. And so basically what we observed is that this MBISA method, but because it is more complex with the shell atomic densities, is longer to converge, whereas the LISA is longer to converge in terms of iterations than the GISA. But the GISA, remember, is the one which breaks the variational structure, and for which you cannot guarantee that the entropy decays. And when you look at the values of the entropy, limit entropy, so here the value of this limiting entropy is larger than for the ISA and LISA method. So we did the same thing with the chlorium oxide ion here, and the results were basically, the constatation were basically the same as for the CO molecule. So just to summarize, so we tried to understand a bit the mathematical structure of some numerical schemes, more specifically the one based on this ISA method, in order to partition molecular electronic densities into atomic contributions. And this ISA method has nice mathematical structure, and so we can say some things about it, about numerical, this fixed point algorithm I told you about. And inspired from these mathematical structures, that's why we introduced this simple discretized version of the algorithm. But of course, there is a lot of remaining open questions. This is just the beginning of the story. So there are some theoretical open questions that remain. Convergence of the full continuous isoprom, original one. Can we get some rate of convergence? They seem to be quite nice for this simple system, so is it always the case? And this is related to your question. How to choose efficiently the basis functions. This is a key feature of the efficiency of the method, and it remains, there's still work to do to find clever ways to do that. Also, the effect of numerical integration. Is it important or not at some point? How to cleverly choose a number of quadrature points to be as efficient as possible. And of course, related to the title of the workshop, here, the large-scale feature is definitely missing in the simple numerical test I showed you. How could we define some kind of more efficient algorithm, perhaps not based on this fixed point loop that I've told you about, but still who would exploit this nice variational structure, which would be able to handle more large-scale and more complex molecules. That's what we would like to think about in the future. And lastly, there's a quite open question for me. So this ISA is a good mathematical structure, but is there a way to say that it is physically relevant in the sense that it will produce good partial charges for a given system? It's an open question. I don't know at this point. There is this kind of principle that this local atomic contributions has to be close enough to their spherical average, which is kind of the common philosophy behind this, most of these AIM methods, which kind of makes sense. But is it enough to have some physically relevant results? This is a good, an open question. So with this, I'll stop here, and I thank you for your attention.